Hello, this is a walkthrough of Euclid's algorithm and extended Euclid's algorithm. So question 1 is asking, prove that for a greater than b, if the greatest common divisor of both a and b is equal to some number d, then it's also true that the greatest common divisor of both b and the remainder of a mod b is also equal to d. So if a is greater than b, we could write a is equal to some multiple of b plus a remainder. We can also see this visually where we have b itself, and then a is, for example, let's just say is 2 multiples of b plus a remainder. So if the GCD D divides both a and b because of the definition of greatest common divisor, then based on this, D has to be able to divide the remainder a mod b because a and bq are divisible by d. So how can we see this? Since GCD divides a and b, then a is divisible by d, bq has to be divisible by d as well, since b itself is divisible by d, thus any multiple of b has to be divisible by d. In order for a to be divisible by d as well, then bq and r, when added together, both of these terms has to be divisible by d in order for a to be divisible by d. Thus, we could rewrite this to be the greatest common divisor has to be able to divide b and the remainder. Question 2 is asking, run Euclid's algorithm to determine the greatest common divisor of both 6 and 32. So running Euclid's algorithm, we usually denote the larger number first and the smaller number second. So when we write this, we could rewrite 2 the remainder as GCD of 6, 32 mod 6 to get the remainder. So 32 mod 6 is 2 because 6 can go up to 30, and then we have 2 as a remainder. After this, we could flip these numbers to get GCD of 2, then take the remainder of 6 mod 2, which is 0. So once you reach 2 and 0, anything with 0, you know that the greatest common divisor is the other number. So in this case, GCD of 2, 0 is 2. Part B is saying, run Euclid's algorithm to determine the greatest common divisor of 13 and 21. So as usual, we run the Euclid's algorithm where we denote the larger number first, smaller number second, and then we flip them around to get 13, find a remainder, 21 mod 13, which is 8. So GCD of 8 and the remainder of 13 mod 8, in this case, is 5. So we flip these numbers around to get GCD of 5, and then we take the remainder of 8, which is 8 mod 5. 8 mod 5 is 3, and then we flip it around to get GCD of 3, and then 5 mod 3, which is the remainder. We get 2 in that case, so we get GCD of 2, and then we take the remainder again, 3 mod 2, which is 1, flip it around, get 1 here, and then we do 2 mod 1, which is 0. Once we hit GCD of 1 and 0, we know that 1 divides both 1 and 0, thus the GCD is 1. Part C is asking us, use the extended Euclid's algorithm to find two numbers a and b such that 13 times a plus 21 times b equals to 1. So what we do is take our equations from part B and take the remainders, 21 mod 13, 13 mod 8, 8 mod 5, 5 mod 3, 3 mod 2, and 2 mod 1 into actual formats of AQ plus R. So when we do that, we know that 21 mod 13 is equal to 21 equals to some multiple of 13 plus a remainder. In this case, we use 1 multiple of 13 plus 8 for 21. We do the same for 13. 8 times 1 plus 5 equals 13 for 13 mod 8. And then we do for 8 mod 5 as 5 times 1 plus 3. And then 5 mod 3 as 3 times 1 plus 2. And then for 3, we get 3 mod 2. We set 3 to be 2 times 1 plus 1. Now that we have the formats of our mods, then we can rewrite these based on the remainders. So we flip these around, we get 8 by itself, so we get 21 minus 13 times 1. And then we do this for the rest of your equations. So we get 5 is equal to 13 minus 8 times 1. 3 is equal to 8 minus 5 times 1. 2 equals to 5 minus 3 times 1, and 1 equals to 3 minus 2 times 1. So once we get these equations right here, we could try to rewrite these, bringing it back up. So we know that 1 is equal to 3 minus 2 times 1, and we already know what 2 is. 2 is equal to 5 minus 3 times 1, so we can substitute this equation right here into 2. Thus we get 3 minus 5 minus 3 times 1, and we simplify this to be 3 times 2 minus 5 times 1. Based on this format, we could try to substitute 3, which is 8 minus 5 times 1. So we substitute 3 for 8 minus 5 times 1, and then we do times 2 minus 5 times 1. We simplify it to 8 times 2 minus 5 times 3. And we want to go back up, so we know that we want to use 5 equals to 13 minus 8 times 1. So thus we rewrite 8 times 2, and then we substitute the 5 with 13 minus 8 times 1. And then we multiply by 3. We simplify this to get 8 times 5 minus 13 times 3. Now the only equation we have left is 8 equals to 21 minus 13 times 1. So we substitute the 8 with 21 minus 13 times 1 times 5 minus 13 times 3. We simplify this to get 21 times 5 minus 13 times 8, which is what we have right here. So we found out that B in this case is 5, and we know that A is negative 8. Part D is asking, given your answers to the previous parts, is there a multiplicative inverse for 13 mod 21? If so, what is it? Similarly, what is the inverse of 21 mod 13? So we know that a multiplicative inverse only happens when the GCD of two numbers is 1. So the GCD of 13 and 21 we found in part B is 1. Thus, there is a multiplicative inverse. So to find the inverse of 13 mod 21, we rewrite our form of 13a plus 21b equals 1, which is 21 times 5 minus 13 times 8 equals 1 from part C. So when we take mod 21 on both sides, we can cancel out this term since it is a multiple of 21. Thus we are left with 13 times negative 8, and then 1 mod 21 is 1. And then now you can see that in this form is similar to what our form of a multiplicative inverse, which is x times the multiplicative inverse equals to 1 mod m. So our multiplicative inverse of 13 will be negative 8, but in mod space we only can go from 0 to 20 in this case. So from negative 8 to mod space, we just add 21. So 21 minus 8 is 13. Thus, the multiplicative inverse of 13 is 13 itself. For the inverse of 21 mod 13, we could rewrite our form 21 times 5. 13 times negative 8 equals to 1. We take mod 13 on both sides, where this term cancels out. And then we left with 21 times 5 equals to 1 mod 13. Now, because of this, we find that the multiplicative inverse is 5. Note that 21 in mod 13 is also 8. Thus, 8 times 5 is 40. And 40 mod 13 is equal to 1, since 13 can go up to 39. Alright, that is all for extended Euclid's algorithm and understanding Euclid's algorithm. Thank you.